go.
Yep, I just started the recording, so whenever you feel ready.
Okay, cool. Yeah, so if you guys, for those of you who haven't met me before, my name is Joe DeMacy. I'm a principal consultant at Bishop Fox. I currently manage the Red Team practice at Bishop Fox. I've been at Bishop Fox a little over 11 years now. I went to UAT in the Phoenix area. I don't necessarily recommend the school, but I did live in the area for a while. I'm familiar with ASU and stuff. I lived in ASU housing, so I had a lot of friends that went to ESU. So, but yeah, so I'm just going to talk a little bit about sort of C2 design considerations to start off with, and then we'll go into Sliver, which is a C2 framework that I co-authored, and how we solved some of those problems, specifically in the case of Sliver. The first thing I will say is, there's nothing special about writing a C2. You still apply the same engineering principles, the same engineering methodologies that you would with any application. There's really nothing special about writing malware other than, like use cases and stuff like that. Obviously differ a bit. But a lot of what it takes to build a C2 is the same it takes to build any application. I don't think it really, other than a few obscurities, it doesn't really require any special knowledge to implement this sort of thing. But, I would just, I think that's a good place to start, because I feel like a lot of people have this impression that there's like something special about writing malware or writing command and control frameworks. Really, it's the same stuff. It's the same as writing any application. If you can write a web application, you can probably write a C2 framework. There's really, other than, again, like some stuff we'll talk about is like a little special. But really, what I want to infer on you guys is how to approach solving certain types of problems. And that methodology is the same that you would apply to any application, especially when it comes to application security. So before joining the Red Team, I was on the application security team at Bishop Fox for about 10 years. And I learned a lot about writing and breaking applications, specifically network-based applications and things like that. I really started consulting in sort of the San Francisco area, doing a lot of work for tech companies. And so my introduction to application security was really sort of like all of the hipster technologies. Like I started with AWS and Docker and containers and Kubernetes and all this sort of stuff. So a lot of the approaches that I take are sort of informed by the lessons that I learned doing, a decade plus of application security. And really when it comes down to, again, designing sort of like secure C2, which I'll talk about shortly, it's the same principles. So if you feel like you want to get better at writing like command and control frameworks, all you really have to do is get better at writing code and building applications and stuff like that. There's no like magic sauce or special knowledge it takes to build some of this stuff. So with that sort of preface. And I need to grant Discord access to my screen. Just a second. All right, let's see here. Hopefully you guys can see. Let me start this slide. Can you see the slides?
Yes, sir.
All right, cool. So this is just a modified version of a presentation I gave at LabsCon that dealt with a lot of this, which was like a very expensive conference. So you guys are getting a good deal, I think. So, all right, so some design principles. So I think one of the core principles when it comes to application security is Shannon's maxim. So if you're unfamiliar with Claude Shannon, he basically invented information theory. He coined the term bit and byte. And he was also sort of instrumental in early development of cryptography. Well, not early, sort of like modern cryptography. So, he's sort of like a World War II era cryptography, which is really when cryptography came of age. Prior to that, cryptography was really based on obscurity. It was not necessarily like a mathematical discipline. And around, the First and Second World War is when cryptography really started to become a math discipline, especially with the work of, obviously, Alan Turing on breaking the Enigma, as well as John Nash, who you may be familiar with from the film Beautiful Mind. Nash was the first one to sort of posit that the only thing that matters is sort of the growth of the problem, sort of like the growth of the big O notation, basically around solving a cryptographic equation or breaking a cipher. That's all that really matters. And then Claude Shannon was also pretty instrumental in sort of the modernization of cryptography. And one of his sort of in his writing, he talks about Shannon's maxim, which is also known as like Kirchhoff's principle, specifically in cryptography. But Shannon's maxim is sort of a generalization of that principle, and it applies to a lot of different things, not just cryptography. Which is, when we're going to design a system, we should design it under the assumption the enemy will immediately gain full familiarity with it. Essentially, this is we only care about the worst case when it comes to security. If we don't encounter a worst case, then it's only uphill, or it's only downhill, I guess. So really, when we're designing systems, when we're designing C2s and things like this, it's worth keeping this in mind, because especially with C2s, I guess if there is something about C2 in writing malware and stuff, is that we have an assumption that there is an adversary, which in our case, I'm going to give this entire presentation from like the attacker's perspective, by the way. So in our case, it would be the defenders, the blue team, or the SOC. They're the adversary that I'm sort of talking about here. So, and it's a very good assumption to make here, because what you'll find, especially sort of in professional settings, is you have very intelligent adversaries. You cannot rely on the incompetence of your adversary for your strategy. So we really need to design this in from the ground up when we're building C2s. When you look at a lot of the open source projects, not all of them, but a lot, and some of even the commercial ones, they're often not designed with this principle. Especially when it comes to sort of the cryptographic integrity of the communication and things like that. They often rely just on obscurity, which is definitely a mistake, especially in a professional context. I'm also going to specifically talk about designing C2s for professional uses. There's a lot of other considerations that would go into designing these types of applications if you wanted to use them as part of like a criminal enterprise or something like that. So I'm also going to be mostly talking about this from a professional standpoint, wanting to use these tools as part of a professional red team. And as part of a professional red team, we often gain access to, as this is the goal, and steal highly sensitive information from our clients. We work in finance a lot. We work in tech. There's a lot of intellectual property. There's a lot of money often involved, obviously, especially in finance. Pre-market trade information is very, very sensitive. And we'll often encounter this type of information as part of a red team operation. And so the communication between the agent or the implant, which we're infecting machines with, and our systems needs to be pretty much bulletproof. You never know where your traffic is going to go. Especially with, I don't know how familiar you guys are with things like BGP and things like that, but you never know where your traffic's going to go, especially geographically. There's a lot of examples of, even when you're communicating between two systems in the same country, you have no guarantee that it's going to take the shortest path or stay within the country, unless you control the entire network or something like that. If you're routing traffic across the public internet, you have no idea where that traffic's going. It could go through China, it could go through, well, maybe not Russia right now because like the internet's off there, but you really have no guarantees where your traffic's going to go or who's looking at it. There's also countless examples, and if you read threat intelligence feeds, you will see a lot of instances where threat intelligence analysts are able to just using big data, essentially, analyze traffic and discover campaigns, as well as like what their targets were and what they were able to extract from that target, just based off of things like DNS logs or traffic logs and things like that. But especially when it comes to things like DNS or internet-wide scanning, you can leak a lot of information about your operation if you're not careful. So this is, especially in a professional context, we have to keep this in mind when we're designing this stuff, because the real adversary is third parties in a professional setting, right? We're actually on the same side as the blue team, which I described as the adversary earlier, but really we're trying to help our clients. And as part of helping them, we can't expose their information, right? We can never be a detriment to security, to the security of our clients' information. So it's really important to have cryptographically robust communication and everything when designing these things for a professional use case. So obviously, the first sort of consideration when building a system like this too is what language do you want to use? And each language, programming languages are tools just like anything else. There's advantages and disadvantages to any tool that you use. So here are some of the more common tools that you might consider writing a C2 in. There's C and C++. I would argue this is a very common choice, I think, by novices, in my opinion. I think it's often the worst choice to use C and C++, but there are some advantages to it as well. So we definitely use C. I don't think we really use C++ at all, but we definitely use C in certain instances. But I would probably not build an entire implant off of it unless I had a very specific reason to do it. The advantages of C or C++ to a lesser extent is it is a low-level language. You are directly interacting with memory. You can directly manipulate memory and things like that. This can be quite advantageous at times. However, this is generally always a disadvantage. It's also performant, but performance is almost always irrelevant in pretty much all programming. Other than if you're writing like a video game or something, that's pretty much the only time you're going to care about performance, or maybe a scientific application, or password cracking is probably the only time you're going to care about the performance of code in a security setting. Other than that, performance is pretty much irrelevant. It doesn't really matter if you save 100 nanoseconds because you implemented your implant in C when the network latency is 400 milliseconds. There's really no difference at that point. So C tends to be, I think, not a great choice for writing implants. It's very slow to develop. It's not a productive language. It lacks any memory safety, which can cause security problems, stability problems. It's just having to manually manage memory is almost always a disadvantage. It's occasionally an advantage, but you also do get relatively small binaries, especially with certain optimizations and things like that. But it also, these languages also lack a robust standard library. I don't know if you guys have ever tried to statically link against things like OpenSSL, but it's kind of a pain. So you generally don't have. It's also difficult to abstract operating system operations in C and C++. You often have to write platform-specific code, which limits your cross-platform ability, which is often also a disadvantage. And there's essentially no dependency management or any decent dependency management in C and C++. So you often incur significant overheads in development time for not a lot of advantages. A much better option is typically Rust. Rust is also fairly low level, but doesn't incur, but is still memory safe. It's relatively productive. It does kind of have a steeper learning curve than other languages, especially Go, but you can preserve a lot of the advantages of something like C and C++ without incurring many of the disadvantages. Typically, the disadvantages to Rust are, again, not much of a standard library. There's 4 TLS implementations, 2 of which are unmaintained. There's really a kind of a fractured ecosystem. around the crates. There's at least like cargo, which is like what you're going to use to build and manage dependencies and stuff. But around like what HTTP library and stuff you want to use, it has a pretty fractured ecosystem. It's occasionally an advantage because you get weird implementations of stuff that can be nice to have. But Rust is typically a much better choice, especially for the agent. Now, when it comes to the server, I don't know if I would still choose Rust in that case. There's no reason you need to use the same language for the server and the implant. So I think Rust is typically a pretty good choice for the implant, but I don't think it's as good of a choice when it comes to implementing things like the server. So Go is obviously another choice. It's fairly-ish low level. It's a little bit higher level than Rust. It has, a garbage collector and stuff. You can still do things like inline assembly and things like that in Go. It's still a compiled language, but you do incur some overhead from that. Go has the best cross-platform support of any major language. It's static links by default, which is nice, but not always nice. It's a very productive language, and it's, again, memory safe. The primary disadvantage to something like Go is the size of the binaries that it produces due to the static linking by default. Then you have things like Python, Ruby, JavaScript, all your typically, interpreted languages. These are very productive languages. I don't think they're very good for implementing implants, but you would maybe consider them for implementing server. Loose typing is both an advantage and a disadvantage. I find loose typing to be very useful in small projects, but as the size of the code base grows, loose typing very quickly becomes a disadvantage. It makes it very much more difficult to maintain the language. Type hinting and stuff in Python can offset some of this, but type hinting is just hinting like the name implies. Packaging these languages is also kind of a nightmare. You typically have to do something like Docker, where you're shipping like gigabyte containers and things like that, just to avoid having to deal with the packaging in these systems. So not a bad choice for the server, but I definitely wouldn't recommend implementing the implant in them unless it's just a toy implant. You would probably never implement something in a professional setting using Python for the implant. Again, the server, not a bad choice there. And then you have something like Java. This is maybe like personal bias, leaking through, but I don't think Java is useful for anything. So I wouldn't recommend using it. The main disadvantage to Rust. So I don't know if there's any like religious Rust people. So Rust is like this, it attracts like this religious fervor, unlike other languages. Where people think it like solves every security problem and has no disadvantages. This is not the case. It's a very useful language, especially in certain use cases, but it's by no means magical. You can still have security problems in Rust. And the other primary downside that I don't think people talk about is the ownership and lifecycle of objects. And a lot of the language features in Rust are very difficult to learn if you're not already familiar with like other programming languages and stuff. I don't think it's like a good first language. And this is often a barrier to being productive in the language. And that's also, I think, a consideration, especially in a professional context where you really need to be leveraging productive languages because if you can't ship it, it's not useful. If you never finish it, if you never get it into an operational state, then it's obviously not useful. So Rust is a very useful language. I like the language a lot. We use it a lot at Bishop Fox, but we use it in very specific circumstances where we think we can leverage its advantages. And I would recommend you guys look to do the same. It's not necessarily like this magic hammer that solves all problems. So this is typically how we get the best of both worlds, though. And this is how Sliver is actually designed to be used, although not a lot of people use it this way. So typically in a real world situation, you're not going to just like YOLO your entire payload at the target. What you're going to have a staging system. So you're going to have a stage 0 or stage 1. Stage 1. So stage 0 would be like shell code, or like maybe you're executing a single command or something like that. But it's basically what just kicks off the process. You won't always have a stage 0 depending on how you're achieving code execution. You may or may not have a stage 0, but you'll typically always have a stage 1. And this is where we really leverage languages like C and Rust. And what all the stage 1 is going to do is load the primary payload, which is your stage 2 payload. It has enough code to talk to the network. It's probably going to have things like compression and encryption built into it. And all it's going to do is download the primary payload, load it directly into memory, and execute it. And that's all you need from it. And this is really where it's often platform specific as well. You're going to be leveraging operating specific functionality because typically your stage 2 is going to be a DLL, a dylib, or like a shared object, depending on the operating system and stuff. But you're going to use some type of shared library as your primary payload. And this C or Rust code is basically going to load that library and then pass execution to it. And then obviously the server can be implemented in anything. But this is typically what we would use at Bishop Fox. So you maintain a small file size. The stage 1 is the only thing really getting written to disk. Your stage 1 is your only exposure or your primary exposure to antivirus and EDR products as well, because you might, or you may or may not, depending on your stage 0, but you'll probably have to write your stage 1 to disk at some point. And so you want like disposable small stage 1s that you can rotate through as they get burned and things like that. And they don't contain a lot of code, and you typically want them to be small so that you can leverage them in situations where you might be concerned about file size. You're not always going to be concerned about file size, in which case you might be able to just jump straight to stage 2. But this is typically what you're going to see in a real-world operation. Because once you achieve code execution, if you're loading things directly into memory, it's very difficult to detect. This is also why we're kind of able to open source Sliver, is because on real operations, we only ever load it directly into memory. We never write a Sliver payload to disk on a real-world operation, and we never send Sliver payloads like in the clear text. They're always encrypted or compressed and things like that. So our exposure to detection from antivirus and EDR is basically, at least when it comes to Sliver, is in-memory detections, of which there are very few. And then our C and Rust our stage 1s are all, private closed source stuff. So those typically never get signatured or anything like that. And so we're able to sort of open source the primary implementation while maintaining this sort of like level of evasion and things like that. So of course, that also begs the question of like, what protocols do you implement? HTTP is definitely going to be, again, in a professional setting, you need HTTP at a minimum, because this is obviously the most common protocol you're ever going to encounter on the internet for the most part, but certainly in sort of a commercial environment, there's going to be a lot of HTTP traffic going around. HTTP also has the advantage of being potentially indirect. So especially in more sophisticated organizations, what you'll typically see is you cannot establish a direct TCP connection out of a network. The only way out of the network is through an HTTP proxy. So this takes line-of-sight networking protocols like neutral TLS and WireGuard just off the table in a lot of these types of corporate environments. A lot of cloud environments don't have as strict egress filtering, and these protocols are often more useful in those types of environments. But sort of like in a more traditional sort of like corporate environment, you're almost certainly not going to be able to establish a direct TCP connection to the internet. You have to go through something like a TLS intercepting proxy. And this is why HTTP tends to be the most commonly used protocol when implementing C2 that's used on red teams. Because of this, it's potentially indirect, right? Like I can send HTTP traffic through that proxy. As long as I structure it in kind of an interesting way, it's probably not going to get detected. And it's moderately performant, right? Like people get frustrated when the internet moves slowly and they can't go to certain websites and stuff like that. So you typically have a fairly high performance connection. Although, barring HTTP 2 and HTTP 3, it's a request response protocol. So there's some nuance in the way that we need to implement real-time communication if we want to implement real-time communication. But for the most part, you'll need this at a minimum. The primary disadvantage is that it's very easy to analyze, especially statistical analysis can often detect things like beacons without even being able to know where, without sort of traditional signatures or anything like that. JA3 detections are also, they're not super common. We don't really see them as much, but JA3 and JARM are where you fingerprint the TLS cipher suite packets in a TLS connection. And that's often very useful for fingerprinting certain types of software. So for example, Meterpreter has a unique JA3. And so if an organization is looking for JA3s on their network, they can detect Meterpreter connections with pretty high accuracy without even knowing what machine that traffic is coming from. And no matter how much you obscure it, if you're using that connection, like it'll detect it. These are also pretty brittle detections, though, and they're easy to tamper with. So, but you have to be a little careful of that. DNS is also pretty much your only other option for indirect C2 communication in sort of like a commercial or professional environment. It's extremely slow. You can pack up to maybe 180 bytes per packet. So at least in a request, in a response, you can put in more. We'll talk about that later. But the primary disadvantage to DNS is that it's trivial to detect if they're looking for it, but often they're not looking for it, and so it's still pretty useful. It's just really slow. But if they are looking for it, you will get detected very quickly. The other main disadvantage to implementing communication over DNS is the DNS RFC, or the protocol spec, is basically not followed at all anywhere on the internet. That like everybody does their own thing for the most part. A lot of resolvers will ignore TTL values, will fake responses. It's a bit of a dumpster fire when it comes to implementing it. So there's a lot of stability considerations that you have to put into your implementation to work around these sort of like very common sort of non-spec compliant use cases, which is why it's not like as common. There's like DNS Cat, Cobalt Strike supports DNS, and Sliver also supports DNS. But I can see why a lot of other projects don't go to implement it, because it's very annoying to implement something that's like usable. So mutual TLS and WireGuard are great options, but they do require line of sight networking. So depending on the environment that you're operating in, they may not be the best choice. WireGuard is pretty awesome, though. It's very performant. It's very difficult to fingerprint. We'll talk about a little bit more about that later. So it's a really great option if you can implement it. It's not a very common protocol yet, at least, but it's becoming more and more common as it displaces more traditional VPN protocols. So the main detections that I see for it are just organizations that are doing packet analysis, and they're like, why is there any WireGuard? We don't use it. So that sort of anomalous traffic detection can often play a role in detecting it, even though it's very difficult to fingerprint. So, and then of course we also have to choose a serialization format. This is the format that the messages between the server and the implant will take. A lot of people use JSON. It's not a terrible option. It's a very large serialization format in that it's space inefficient. It's also self-describing in that, like, if it's human readable. Like, if you look at it, you can basically figure out what's going on. This also makes it more difficult to obfuscate. If you have a field in a JSON object called command, and you obfuscate your implant, at some point, the implant still needs to read that field from the JSON object and know its command. So it can be difficult to obfuscate it, because if you change command to something else, then the implant needs to know that. And so what Sliver uses is protobuf, and what I would recommend using is protobuf or message pack. These are non-self-describing serialization formats that don't contain that. And so if you need to obfuscate a field in a struct or a field in a message, you can very easily do that, because the server and the implant do not need to use the same name for the same value. And they're still able to communicate. So it's very useful from that standpoint. It makes it much easier to obfuscate the code. Especially programmatic obfuscation is much easier with something like protobuf or message pack. Protobuf, the primary disadvantage is the code. It uses code generation. And the code generation is typically not very idiomatic for the language. which is a word that programmers like to use to sound smart. What it means is like it's not really like it doesn't conform to the standards of the language, or it doesn't take advantage of language-specific features or conventions in the because it's generated code. So, for example, if you use like the Python protobuf library, it'll generate a bunch of objects that don't really conform to the way you would normally structure a Python object. So it's a little annoying to work with from that standpoint, but it's great. It also allows very easy cross-language support because it's using code generation. You can generate Go definitions for the server and Rust definitions for the implant, or C definitions for the implant if you want to use C for some reason. And message pack is kind of similar, but there are other serialization formats, but I probably wouldn't recommend using them, and you'll probably switch to one of these at some point. Anyways, if you do use JSON, make sure you compress it in order to get that space-efficient encoding. So, but I think protobuf is one of the better options, to be honest. And I would probably recommend using protobuf in most cases. Really, the main disadvantage is just that code generation piece. And then there are sometimes slight inefficiencies in the way the generated code works, which can contribute to file size and stuff like that. But it's a data-only serialization format, so it's pretty safe from a security standpoint, and it's not self-describing, and it makes obfuscating things pretty easy. So definitely take a look at protobuf. And it's great. It works over HTTP or a variety of protocols because it's so space efficient. So. All right, so let's get into some examples. So I want to talk a little bit about Cobalt Strike. Cobalt Strike is actually a pretty good framework. We do use it on occasion. It is a sort of Windows specific. I mean, you can make it run on other platforms, but it's not really designed to, so you don't really want to. So it's primarily, a Windows implant framework. If the environment that you're targeting doesn't have Windows or not a lot of Windows, it's probably not a great choice. But if you are targeting sort of a Windows-heavy environment, it's not necessarily a terrible choice. However, it does have everything basically tries to detect it. And so you basically have to put in a lot of effort to obfuscate the payload in order to get past things like EDR and antivirus, just because there are so many, even in-memory detections for it, that you often will expend more effort obfuscating it and getting it to load onto a target than just like writing something yourself. So it's not a bad framework. It's been kind of a victim of its own success, though, in recent years. And yeah, it's kind of a pain to use these days because you have to do so much obfuscation with it. So, but aside from that, like I was saying earlier, there have been a number of security problems with Cobalt Strike as well. So this is kind of the first one. So these are all fake sessions. So So for a long time, and this is kind of it is still kind of lacking. It's a little nuanced, but basically. When you're designing an implant, you definitely want to implement mutual authentication, which means that the server verifies the implant in the same way the implant verifies the server. And in this way, you don't, basically this is called Cobalt Strike Spam. And it's basically a program that you can run that'll just go around the internet looking for Cobalt Strike servers, and it'll just spam them with fake beacons so that the server basically becomes unusable. And the reason it can do this is because Cobalt Strike kind of has weak mutual authentication when it comes to its traffic. And so if you can pull the server config, it's very easy to parse out the public RSA key from the server, which is all you need to communicate with the server is its public RSA key. And then from there, you can just send it lots of random information and do stuff like this. You do at least need the RSA key. So if the attacker doesn't have, or if the adversary does not have an RSA key, they can't spam the server. But for a long time, Cobalt Strike exposed its stage, right? So it also uses like a staging mechanism. And you could easily pull the RSA key out of this staging mechanism, which was enabled by default. So if you do use Cobalt Strike, make sure if you're not using the staging to disable it or obfuscate in such a way that the stage 2 payload cannot be easily retrieved because you'll run into things like this. But I think the main lesson here is you definitely want to be implementing mutual authentication. You do not want to accept any traffic. This has the added benefit of just generally improving security, because it minimizes the attack surface of the server as well. So, and the way this works in Sliver is sort of the fundamental principle that we implemented in our C2 protocols is the server does not respond to any traffic which it cannot cryptographically attribute to some code that we generated that came from our server. And we'll talk a little bit more about that in the fingerprinting, but this also reduces sort of like the fingerprintability of the server, which is very important. So there's also recently a remote code execution vulnerability in Cobalt Strike through the Swing library. Again, don't use Java. Like, it's a terrible programming language. So, all right, so anti-fingerprinting. So one of the other important things in a professional setting, if you want to run a criminal enterprise and infect, like, grandma's laptops and things like that, you don't really have to worry about this. But in a professional setting, you're often working against organizations which have threat intelligence operations, threat intelligence analysts. And a lot of the strategy these days is sort of threat hunting. And this is where an organization will basically constantly be looking at what's on the internet and identifying known malicious IP addresses and domains and things like that, and just straight out blocking them. So this can often get your operation burned before you even send a payload or an email or do anything. Because it's so easy to scan like the entire IPv4 internet that as soon as you put up a Cobalt Strike server, for example, if you just started a default team server on the internet, it would get fingerprinted and identified as a malicious IP within a few minutes, probably. Well, maybe like an hour or two, but pretty quickly you're going to be identified as a malicious IP, and that IP is going to work its way through a bunch of threat intelligence feeds and often be blocked by an organization before you even send a payload, before you send a single message. And so it's very important in a professional setting, if we want to target professional organizations, that it's difficult to identify the server as malicious. And the easiest way to identify servers as malicious is sort of interacting with them and fingerprinting them. And this is, again, things like JARM, the JARM, which is the hash of the order of the TLS ciphers, is often used as this. They'll also look at things like what is the order of the response headers, what response headers are, assuming HTTP, what response headers are included, and they'll probe servers with certain types of HTTP requests in order to look at the responses and figure out if it's malicious. So this is, again, where that mutual authentication becomes very handy, because if we can cryptographically attribute a request to the server, then we can just not respond, or respond with like an empty 404, which is what Sliver does, which is very difficult to fingerprint, right? As soon as you elicit application-specific functionality in a response, it's very easy to fingerprint that. The other thing to consider here is if we are doing some type of key negotiation, which you typically would want to do because we want to use ephemeral keys that are never written to disk to encrypt the communication, you need to use a single round-trip key exchange. So other open source frameworks, so for example, like Merlin uses like Opaque, which is like another popular open source C2 framework. Opaque is a perfectly secure key exchange mechanism. However, it requires sort of like a three-way handshake in order to negotiate the key, which can be fingerprinted because the server has to elicit a response to sort of the initial key negotiation request. Pre-shared RSA kind of fixes this, but not always, depending on how you implement it. And then there's a variety of other key exchange mechanisms. But the important thing is anytime you're implementing a key exchange mechanism, again, at least in a professional context, it needs to be a single round trip. As soon as the server receives a request, it needs to be able to figure out if this is a valid request without, there can't be any back and forth. You need to be able to do it in a single request. So that's an important thing to consider when you're designing the security mechanisms. So, in Sliver specifically, again, we cryptographically attribute all of the traffic to binaries that we generated. or we use mutual TLS, where there's client certificates that we signed that must be provided by the implant. Otherwise, we don't, respond. WireGuard by default uses a single round trip key exchange, which is very useful. You actually cannot scan the internet for WireGuard endpoints because they will just not respond to any packets that are not cryptographically attributed or cryptographically authenticated by the server. So this is also very useful because you cannot scan the internet for these endpoints like you can an HTTP server or something like that. Mutual TLS is also very useful because the responder will only get a very generic JARM for that because they won't be able to provide a valid client certificate, at least without extracting it from an obfuscated beacon. But that beacon has to come from our server. So with HTTPS and DNS, the way Sliver implements this is we have sort of like a TOTP hello that we use, but we also use Knucklebox or Saltbox, which is an ECC sort of encapsulation. It uses Diffie-Hellman and stuff, but it's like a well-vetted cryptographic exchange mechanism. And then we sort of put TOTP on top of that because TOTP is very easy to implement. And the values change. So the other nice thing about TOTP is the values expire every 30 seconds. So even if you get an identical URL from a key exchange and you replay that against the server, if it's more than 30 seconds old, the server will just reject the key exchange request because the TOTP is invalid. And then we use Cha-Cha-20 Poly 1305, which is an authenticated cipher mode for all the symmetric encryption. We also store the SHA-256 of every ciphertext which is exchanged or sent in order to prevent replay attacks. So this is a common mistake you'll see in a lot of C2 protocols is they don't necessarily, it might be encrypted properly, but they won't prevent replays. So you're able to replay commands and things like that. So, and often, even in between beacons, you can replay certain things. So if you get a kill packet, you can take that and just start spraying it at other implants and kill them basically. So this is also often problematic with the server. If you can replay messages to the server, there's often security implications of that as well. So think about replay as well and whether or not that's going to affect your protocol. And then we randomize the JARM and Sliver, but that's pretty easy depending on the language that you use. So kind of jumping more into the design of Sliver specifically, as you guys might be aware, it's written in Go. The inspiration for Sliver was the Trusting Trust document, which was written by Ken Thompson. Ken Thompson is an OG Unix hacker. He invented the C programming language to some extent, and he's one of the main inventors of Unix, but currently works on the Go programming language. And he wrote a really great paper back in 1984 that describes backdooring a compiler. And I really liked that idea. And so I initially tried to write an implant that contained a compiler and was able to recompile itself. I kind of got that working, but it was 400 megabytes for the implant. So anyways, I ended up embedding the compiler in the server rather than in the implant itself. And that's why you can, that's how how Sliver generates implants and stuff, is it generates the Go source code and then compiles it using the Go compiler toolchain. And yeah, so this is kind of what the architecture looks like. We use gRPC for all of the operator and server communication. gRPC is basically just an RPC implementation of protobuf. And then we take those protobuf messages and we use a lot of the same protobuf messages to talk to the implant, but they're encoded and encrypted using C2 protocol specific mechanisms. But on the operator side, it's all gRPC. But still using mutual TLS. So we use dynamic code generation for the implant, and then we do per binary encryption keys and other values. This is, again, how we're able to cryptographically attribute any traffic that the server receives to a binary that it created. Since we generated those keys ourselves and we inserted them, we can be quite certain of that. And this also allows us to dynamically remove debug code and any unused code or unused functionality, depending on the generate command, will actually remove code from the implant as well. We do C2 over mutual TS, HPS, WireGuard, DNS, and then pivots over TCP and SMB. And then, of course, all your sort of typical cross-platform stuff. One of the main drivers for using Sliver or developing Sliver was Bishop Box has a lot of clients that do not have Windows in their environment, and so we needed something we could target macOS and Linux with, in addition to Windows. And so that's kind of why we ended up choosing Go, is because it has such great cross-platform, and we've extended that through the build mechanism to compile to a number of different artifacts and architectures. That sort of stuff. Support side loading, so we can dynamically load libraries. There's beacon object files, support in-memory.NET execution. This is all the stuff. This is the advantage of having like a larger stage 2 payload, is you can implement a lot of this rich functionality in the stage 2 payload because you don't really care about its size, right? Stage 2 payload can basically be any size you want because you're loading it over the network, dynamically using your stage 1. You never write it to disk. You never have to embed it in anything. And a few megabytes on modern networks is really, nothing. So let me just kind of skip ahead. So this is an example of an HTTPS request in Sliver. We encode a variety of information. So the other thing to consider when you're designing your C2 communications is whether or not it can be matched with like a regular expression. And you definitely don't want that because basically all the hunt tools rely on some type of like regular expression or query mechanism or pattern matching. So if you can just break the pattern matching, or if you basically make it very difficult to hunt. So one of the goals in implementing the HTTP communication, which if you remember back to the advantage and disadvantage slide, can be very easily inspected, is that we never want to send the same value twice. There should be no discernible commonality other than like maybe a static header like a user agent or something that you would expect it to not change between two requests, because in typical HTTP communication, you're not going to see a lot of overlap, as well as, we can sort of break this pattern matching stuff. So the first thing Sliver does is it randomizes the URL path, because in HTTP, the URL path is just a string. It has no actual meaning. A lot of people associate this with like a file system path, but it's really just a string in a request. Like it means nothing to the server, or it means nothing to anything. Unless whatever meaning you give it. So we just randomize that. Like it just does not matter. And then we just build that random path based off of common strings that you'll see in HTTP traffic. The only thing the server looks at is actually the file extension. So the file extension, in this case .js, indicates the type of request that we're sending. A .js in this case is a polling request. The next thing is the nonce. So we also include a nonce, which identifies the encoding mechanism. So we also randomly select an encoder to encode the data in the request. However, the server has to be able to identify the type of encoder that was used to randomly encode, the request. So in this case, this nonce, this numeric value, is the one that identifies the encoder that was used. And we have constant values that identify these encoders. But like I was saying, we don't want to send the same value twice. Like if the encoder ID was like 64 and we were sending 64 in every single request, you could pretty easily write like a regular expression rule to just look for a lot of requests with 64 in a URL parameter. So we don't want that. So what we do is we take some other random value and we multiply it by a modulus that we know, and then we add the encoder ID. And this creates some random integer value. And then when the server receives that nonce, it basically reapplies the modulus to the random value, and then it gets back the encoder ID. And then, so we can use static encoder IDs and a modulus times some random value. And this way, in every single request, this numeric value is going to be some random integer, and it'll never be the same. But even though it's communicating potentially the same thing. And then we also use cookies to store values and things like that in the request. So This is why if you ever look at like Sliver traffic through Burp or WireGuard or something like that, you'll see a lot of every request is different. And it's never the same. And even the numbers that identify the request are random in each one. And the way that we find the nonce is it's any single character argument, URL argument, right? So we also encode information in the length of the arguments. So 2 character URL arguments are interpreted as TOTP values, and then 3 characters or more are just ignored, and you can actually randomly add 3 character arguments to the traffic, even though it's not used, right? So even though it's not used, you can just add that extra entropy to the request to make it more difficult to hunt. So that's another thing to consider when designing communication mechanisms, is how to add extra noise to the communication in order to make it more difficult to hunt in environments, even if you're not necessarily using that stuff. So I think this is a video. So this is Burp. So what you can see here is all of the single character. You can see all the single character arguments there. So I'm going to just generate some traffic here through Sliver. So I'll like open a bidirectional shell here and then run top so that we're constantly generating traffic here. So you can already see all of the numbers that identify the encoder in the request are different for each request. We also randomly insert alphabetic characters into the nonce that are just ignored. And then you can see here it's randomly selecting different encoders. So this is the English encoder that encodes binary data into English text. So that it's randomized every time. So no request basically that contains an actual parameter has a duplicate value. Even if we're sending the same value, it'd be completely different between 2 requests. So this brings us to DNS C2 communication. I swear I'm almost done. How am I doing on time? All right, I think I'm doing okay on time.
Yeah, you got plenty.
Okay, cool. So the way DNS works, right, is we basically... Here's the thing, like DNS is a dumpster fire of an ecosystem. It's ostensibly a case-insensitive protocol, so upper and lower case shouldn't matter. However, some resolvers will just take whatever case you specify in a domain and convert it to all uppercase or convert it to all lowercase. Or it may not. It may just not touch it at all, which is what the protocol specification says you should do. But I've also seen other resolvers that will like randomize the case of the request. I suspect to encode data into it as well. But anyways, so when we want to establish a communication channel over DNS, we basically have to encode data into a subdomain within a URL, like within a domain name, right? And we don't necessarily know ahead of time if we're going to be able to use a case-sensitive encoding. So the one that you're probably most familiar with is like base 64. However, there's only 62 valid characters in DNS, so you can't use base 64. But it's a much more, if we can use it, the more characters we can use, the more efficient the encoding, right? So if you think about hexadecimal encoding, there's 100% penalty incurred because you're using 2 bytes to represent 1 byte, right? Base 64 is a little bit more, I think it's like 30% efficient or something like that. That is to say, the size of the message will be 130% of the original size. And base 64 has the added benefit of, right, it can encode arbitrary binary data into the ASCII character set. That's what it was invented for. And it's fairly efficient at that. But we can't use it because it's 64 characters. We could potentially use base 58, right, because the number base is arbitrary. You can have base any number. You could have base 1222 or something like that. Encoding doesn't really matter. It's arbitrary. 64 is just convenient. But base 58 is also a common encoding. It's actually used pretty common by Bitcoin a lot. The Bitcoin protocol uses base 58. The problem is it's case sensitive, right? It's using upper and lowercase characters as part of the encoding mechanism, and it's using upper and lowercase to indicate different byte values. And so if we do encode with base 58 and we send it through one of these rude resolvers that messes with the case of the request, the data will get corrupted when it gets to the server, and it corrupts our communication channel. Pretty much all the other implementations I've seen use hexadecimal encoding, which is not case sensitive, right? Because we're only using 0 to 9 and then A to F to encode, and we can interpret A to F, upper lowercase, as the same value, right? So that's case insensitive. So we could use that, but it's literally 100% inefficient, right? It's doubling the size, and we're already talking over a protocol which is quite slow. So base 32 is sort of a good option here because it's a more efficient encoding mechanism, which means we have to send fewer DNS packets to send the same amount of information, and thus it speeds up the communication channel. And base 32 is also case insensitive. So it uses alphanumerics plus a couple symbols, and you're basically good, right? So we gained some efficiency by just switching from hexadecimal to base 32. But Sliver also plays a couple tricks here. So the other thing Sliver does is when you start up a DNS communication channel, what we do is we generate random data, and we base 58 encode it, and we send it to the server. And the server responds with the CRC32 fingerprint of the data that it received. Because CRC32 is 4 bytes, and an IP address is 4 bytes. So we can so it basically responds as an A record, as an IP. But we basically just interpret the CRC32 as an IP address, right? Because they're both 4 bytes. But this allows the implant to basically detect whether or not it can use a case sensitive encoding like base 58, because we can tell whether or not the data that we're sending is the same data that the server is decoding on its side. So if some resolver is messing with the case of the DNS packets that we're sending, we can detect that and then fall back to base 32. Otherwise, if we detect that there is no corruption, we can just stick with base 58 and gain further efficiency in the communication, because we're, again, able to encode more bytes and send fewer packets. So this is kind of what it looks like. If you just run it Sliver implant in debug mode, you'll see something like this. You can see here in the subdomain, this is the data that is being encoded by the implant. This is kind of just a hello or a random packet. And then the server, this IP address, is basically the CRC32 of the data that it received. And so you can see this is where it's starting to fingerprint the resolver. Again, we are using a single round-trip key exchange. So we are able to encode a full asymmetric key exchange into the first DNS packet that we send, and then we also encode that TOTP value so that the server can reject unauthenticated DNS packets, because you can scan the internet for DNS servers. And then from there, we fingerprint the resolver to figure out whether or not. And then actually the implant also measures the round-trip time, and will kind of try to load balance across multiple resolvers if they all work. So, but this is what data encoded into a subdomain might look like, assuming 1.littlepeep.rip is our parent domain. This is the base 58 encoded message that we're sending. And then we also include things like sequence numbers and things like that, so that the server we can send messages out of order or in parallel, but the server can still reconstruct the whole message. So we actually add sequence numbers to all of these as well. And then, you can send it across multiple resolvers, send it all in parallel in base 58, and you get a decent connection. It's still not super fast. So you can see here, it fingerprinted the resolver, and this is it polling the server for information. And you can see here, I can open up a shell over DNS, although it's not super fast. And there's a slight hiccup here, I think, although it should catch up in a second. Yep, there we go. So you can see some of the data that's getting sent, and now we have like a real-time, right, I'm running HTOP over DNS. So that's just showing the full bidirectional communication channel that we've built. And it is fast enough to run things like HTOP and stuff, even though it's a little laggy, right? But this is by far the most difficult one. At least I had the most difficulty implementing this one, especially full bidirectional communication is a little tricky to implement correctly over DNS. So I think it's a good learning experience, but definitely be ready for some pain if you do want to try to implement something like this. So that's kind of the end of my slides. I'm happy to jump into like any of the code though, if you guys want to hear about that. Or just I'm happy to answer any questions you guys might have as well. Or if there's anything I didn't talk about, I'm happy to opine on that as well.
I just had a quick question. I was reading through just the GitHub page with the Getting Started tutorial, and I got to the section about implants, where you go into two modes of operations, beacons versus sessions. Could you speak about that a little bit and what benefits you get out of doing one operation over the other?
Yeah, so frameworks differ depending on how they implement this stuff. Sliver implements both, like you said. So the two basic forms, though, are a beacon, which is sort of the Cobalt Strike form of communication, or a session, which is sort of the Metasploit or Meterpreter form of communication. So if you're familiar with those, this probably make a lot of sense. But basically, the way a beacon works is it's going to periodically, so every 5 minutes, or sometimes every hour, or every 24 hours, or maybe even once a week or once a month, the implant will reach out to the server and ask if there's any new commands. And it will basically download those commands, execute them, and then upload the response back to the server, and then it'll go back to sleep for however long it wants to sleep for. This has the significant advantage that the implant or the malware is not connected to the server for the majority of the time that it's running. So if you run something like netstat or something like that, or if you're looking at net flow information on a network, those connections will be very difficult to spot because they're very short-lived, right? You only establish a connection to the server over long periods between large gaps, and you only establish that connection long enough to retrieve the tasks and then upload the results. The disadvantage, obviously, from the attacker perspective is you cannot send commands to the implant anytime you want. Well, you kind of can. So like in Sliver, the way it'll work is like if you type in a command against a beacon, the server will basically store that command in its database, and it'll wait for the beacon to check in, and then it'll send the command to the beacon. So you have like this very asynchronous form of communication with the implants. This is pretty much only advantageous from an operational security standpoint, from a detection standpoint, because it's much more difficult to spot these connections because they're not constant. So conversely, a session is more like SSH, where you have a real-time communication channel with an implant, and as soon as you type a command, it's immediately sent to the implant, it's immediately executed, and the response is immediately returned to you. So Sliver does allow you to switch between these, well, kind of. So a beacon in Sliver can be converted to a session, but a session can't be converted to a beacon. So typically the way that you'll use Sliver, and we use Sliver in an operational environment, is you will generate all beacons. So you'll default to everything that's a beacon. And a lot of commands will just work over a beacon session or a beacon communication, because like if you want to list a directory or something like that, right, you don't really need a real-time communication channel for that. And you might be willing to wait, or if you're running LSS dump, or if you're running Mimikatz or something, right, like you can wait 5 minutes for that to run. Other commands, like if you want to tunnel network connections or things like that, that obviously requires a real-time communication channel with the implant, because obviously TCP is a real-time communication protocol. So for those, you need sessions. So there are certain commands that will only work over a session in Sliver. This is the same in Cobalt Strike. The way it works in Sliver, though, is that you'll use the interactive command. So the interactive command in Sliver basically tells an implant or a beacon to establish a real-time communication channel to some server, which could be the same server or a different server, depending on how you structure it. So sessions are obviously much more time efficient. So if you're in like a CTF or something like that, you probably just want to use sessions because you don't really care. and you're optimizing for time, all the commands will be available to you. You don't have to wait for the implant to check in order to get a response. You can operate very quickly. However, in a real environment, especially if persistence is important, and often in our operations, the goal isn't just to break in, it's to persist and extract information over time from an environment. Beacons are very, very useful for that, and they're much, much more difficult to detect. So in a real world operation, you'll default to beacons and then occasionally switch to a session when you need to get certain things done. Or you'll just do everything over a beacon. So does that make sense? Any questions about that?
Yeah, I have questions about sessions. So Sliver offers like networking features like port forwarding and SOCKS proxies. How do you implement those over like HTTP?
Right. So HTTP is a request response protocol. We want to establish a real-time communication protocol over this. So what we do is we do something called long polling. So if you look at going back to, there's nothing special about implementing C2s. So long polling is actually a mechanism which was built for web applications. So that a browser could basically, like if you were implementing something like Discord, like the web version of Discord, at least, a few years, imagine we're like 5 or 6 years ago. And like, you can't necessarily guarantee the browser that you're running in will support something like WebSockets, right? So we need some way for these older browsers to be able to establish a real-time connection to the server such that the server can push information to the client. That's the other thing, right? Bidirectional communication in TCP, either side can write to the socket. In HTTP, the server cannot push something to the client. Again, barring HTTP 2 and 3, where something like this was implemented, or some other protocol like WebSockets, which is built on top of HTTP, right? So what we do is something called long polling. And the way the long polling works is the client will just send a request to the server. It'll actually send like 2 or 3 requests to the server, and the server will just hold on to those requests. It actually won't respond to them right away. And when the server gets a piece of information or a message that it wants to send to the client, it will basically then take one of those responses and respond to it. And if you're clever in the way that you implement the timeouts for these requests, you can basically always ensure that there's a pending HTTP request that the server has and the server can respond to. And then if the client wants to send data to the server, obviously it just puts it in a request and sends it. So that's the way that it's implemented in Sliver, is we use a form of long polling where we'll actually hold on to the request and not respond until we have data to send. There's also like a timeout, right? So the issue that you'll often run into this is proxies will often have their own timeouts. So you may not necessarily control the entire timeout for a request. So what we do is the implant will basically send, I think it's like 2 requests to the server, and the server will hold on to them for, I think, up to like 2 seconds, and we actually randomize the time, the maximum time that we'll hold on to the request for, until it has something to send back, to the client. And then if it doesn't have anything, it'll just send an empty response, and then the client or the implant knows to immediately send another request as soon as it gets an empty response back. That way, again, there's always some request pending on the server, and the server always has something it can respond to and push something back to the client. And if you Google long polling, you'll find a ton of information about how to implement that. So. But excellent question. We do something similar for DNS, by the way, because DNS is a similar request response type thing. So.
Okay. I got a quick question for you. So what's on the roadmap for Sliver in the next year or so?
Do you want to see some of the stuff I was working on?
Let's see it.
Yeah, I can kind of show you. So actually, the thing that I'm working on right now is password cracking integrations.
Okay.
So what I did is, so right now we have this problem on my team where cloud GPU instances are like kind of expensive. And so we try to use spot instances where you bid on the price of machines. However, like Pixar and a bunch of other major companies like will do this and they'll bid up the price because they're rendering a movie or something. So you can't always get machines if the price is too high, right? And like the system that we use we use an open source application called NPK, which isn't terrible, but it's not like super reliable. And it has a lot of limitations, like you can't upload custom word lists and stuff like that. I'm also lazy. So for those who don't know me, I'm actually really lazy. And I don't want to have to, I'm annoyed when I have to like copy and paste like a hash out of a terminal onto another machine to like crack it. So what I've been doing over the last couple of weeks is I've been implementing basically distributed GPU password cracking functionality into Sliver servers, such that you can just dump a hash from a remote machine and it'll immediately queue it across any number of GPU instances that you have, and it'll crack it. And then automatically, what I want to do after that is like feed that back into lateral movement so that I can automate lateral movement. I can just like drop an implant and say go, and it'll like curb roast accounts, and then like if it cracks anything, it'll like use WMI to like execute payloads on additional machines, and I'll just like get more and more implants. That way, like I can go have a coffee, I can come back, and like half the network will be compromised by the time I get back. So that's what I've been working on. I can kind of show you guys some of the early. So I think I have some of it here that I can show you. I'll need to. So some of this is public if you go around into other branches in Sliver. So yeah, it's in the 1.6 branch. Let me recompile this. And then there's another component that you'll need that's not open source yet, but I will open source it. So it's this crack station thing. So that's this over here. So I've compiled my own version of Hashcat for this as well. And then I embedded the Hashcat binary into the crack station binary. And then it also uses multiplayer, so everything goes over mutual TLS as well. So you can see here, if I run crack stations, it says none are connected. So I can connect one here. Oh, wait, and assuming I didn't break the code, which it looks like I did. Let me add some of this code back. Hold on. This is all still in development, if you can't tell.
Has to Control Z the whole program.
Yeah. Why is this complaining? What util is it importing? Yeah. Wait, is it unzip off? I need to hold on. I copied a lot of this code from Sliver 2. Actually, so the other thing I'm going to do is I'm going to use the port forwarding code in Sliver to wire all of them together for the brain server. So I don't know if you guys are familiar with like brain servers and Hashcat, but it has like this machine learning mode where you can where's unzip off? Oh, shit. Where you can like apply machine learning to, actually, let me just pull it from the old version here. Where you can apply machine learning, but you have to network all the instances together. So what I'm going to do is just basically use the port forwarding to wire all of the machines together as well. But the crack station actually imports code from the implant and stuff. But anyways, that's the function I need. Oh wait, it's already. Yeah. All right. Does that work? Yes. Okay, so if we connect this, and actually, let me see if I might be able to get my other machine too. All right, so this machine is connected now, and I think this is my actual cracking machine, which I think I should be able to connect this to. So Sliver connect big. So it also synchronizes all of the files automatically. That might take a second. So you can see here, I think I have a couple of word lists. Yeah, so you can upload word lists and everything, custom anything you want. It also supports, you can upload custom word lists, custom markup chains, custom rule files and everything. And it'll synchronize them all between the instances. You can see this one's already connected. It'll probably take a second to download. But now if I run crack stations, you can see it's detected my MacBook here in the M1 Metal GPU, and then it's already run benchmarks. So the other thing it does is when a new GPU connects, it'll actually benchmark the system. And then when you go to crack something, it will calculate the difference in performance between the two devices and then load balance the key space for the cracking job between the machines automatically. And that way, all of the tasks should end around the same time, and you don't run into inefficiencies where, like, my 3090 finishes 2 hours before my MacBook or something like that. Okay, so that one's connected now. So you can see here, it's got this one with the NVIDIA 3090. It's also detected the i9 1200K for OpenCL. It has the benchmark for this device already, and then you can find this one. So I don't have the queuing done yet, so I can't show you guys that, but that's kind of where I'm at with this. It'll check in, it'll benchmark, and it'll track GPU instances and stuff like that. So that's kind of what I'm working on right now. But which is awesome. Kind of out of it's kind of out of left field, I feel like. But
automating pen testing as a service.
Yeah, that's kind of I really think, like, so if you're unfamiliar with like the lore from Magic the Gathering, slivers are like these hive mind creatures that like share abilities. And so I kind of like the idea of like all the operators being able to like connect their own thing and like share those resources with the rest of the team. So that's I was like kind of thinking about that, and I was like, what would be really nice to be able to do that is GPU password cracking, because like these cloud instances are really expensive. Their GPUs are fast, but not that fast. And like I have a 3090. Like two of the other guys on my team have like 3090s or 3080s and stuff, and like we have a lot of computation just like sitting on these gaming desktops, but you don't have like a good way to pool them together. And so that's why I kind of want to build this. And then like the crack station also doesn't write like hashes to disk or anything, and all the communication is over mutual TLS. So again, it's very clean from sort of like a professional standpoint. We're not leaking information onto all the devices or anything like that. So, so probably not what you were expecting for the next version of Sliver, but
no, that's not.
Yeah. But I really like password cracking in general too, so it's like a good opportunity to do something, because like there's like hash topless, like there's a few front ends for like clustering Hashcat and GPU instances and stuff, but they all have like their own quirks and stuff. Like hash topless is written in PHP, and like I don't know, the last time I looked at it, there was like a ton of remote code execution vulnerabilities in it. So it's like not great from like a security standpoint, and like I just generally don't trust PHP code. And like NPK is okay, but like you can't upload custom word lists and stuff. So if you want something right, you got to do it yourself, I suppose. So we'll see if mine ends up being any good. I haven't finished it yet, so we'll see. But cool. Any other questions?
Yeah, I have a question. Can you hear me all right?
Yep.
So I take it most implants will still have to write something into disk because, say you hack somebody's work laptop and they want to shut it off, turn it back on. So I got two questions. How do you make it persistent across that? And how would you write a program to check for a C2 implant for memory if you had to, just for one machine, not anything like at scale?
Yeah, so that's like a CCDC question, is that? So for persistence, what we'll typically do is we'll persist the stage 1, and depending on the environment, we may just pull the stage 2 over the network again, or we'll encrypt the stage 2 and then write it to disk. And then when the stage 1 runs, it'll basically read the ciphertext from disk and then load it back into memory. That way, again, the plain text stage 2 is never written to disk. Only your exposure is just the stage 1. Or depending on the machine, we might just re-exploit it. Not establishing persistence is often also very advantageous for an attacker because it's so difficult to detect. So if we're in a position where we can re-exploit a system, we probably won't even bother with persistence, because persistence also often will open you up to detection. Even if you can't detect the implant, sometimes you can detect the persistence mechanism. As far as persistence mechanisms, we use a variety depending on the operating system and, again, the target environment. In a real-world operational environment, we'll typically use DLL hijacking for persistence. We have a number of different methods for deploying DLL hijacks. And then, again, we'll compile the stage 1 as a DLL and then write it to disk that way. Again, that has just the advantage that there's no like run keys or anything like that can be detected. We'll typically try to choose a program that we know is almost always going to be running or is already running at startup, and we'll prioritize those for DLL hijacks. The other option is image file execution options. So we'll often use image file execution options for persistence, which you can Google. That's a fairly well-known method, although we have a few tricks that we play so it doesn't run up or it doesn't show up in like sysinternal tools and things like that. Other times we'll also do LNK files. So there's ways of persisting within LNK files and stuff like that. That's also sometimes a good option. And those are probably the ones that we field the most. There's a lot of different ways. Persistence is kind of its own art, especially across different operating systems. There's a lot of different methods for establishing persistence. We'll also persist through browser extensions in certain cases. We have methods, for example, on Mac OS, where we can persist within the Chrome process by abusing certain functionality within browser extensions. So we'll do that. And then like our code basically runs whenever you open Chrome, which is like always. We'll typically piggyback. We typically will not just like add run keys to the registry and stuff. Although honestly, that is so obvious these days. I feel like it would actually work and no one would notice, just because it's such an overt act that like nothing's probably looking for it. But as far as like pulling stuff out of memory, there are a lot of forensic tools that can do that. So PEsieve, for example, is an open source one that's quite good. Process Hacker, although I wouldn't necessarily recommend using Process Hacker in something like CCDC because it loads its own driver, which allows you to like kill EDRs and stuff. So, so threat hunting is its own discipline too. And I certainly understand, I have very basic skills when it comes to threat hunting, right? I should actually probably get better at it. But in my opinion, though, when it comes to the type of work that I do, if a human is already looking at a certain process or looking at a certain file, we're already screwed, right? Our philosophy or our strategy is basically, if you avoid the automated analysis, a human will never see it. So it doesn't really matter if a human can look at it and figure out if it's malicious. What we care about is like, can a machine look at it and figure out if it's malicious? So that's kind of a key difference between things like what we do and something like CCDC, or if you're doing like incident response or something. Like PEsieve is a really good one. It can pull stuff directly out of memory. That's probably the one I'm most familiar with. Other than Process Hacker is really good. The entire suite of sysinternals stuff. Although pulling stuff out of memories is tricky because like we overwrite the headers, and we overwrite the PE headers and stuff. So like you have to like go in and like pull like the sections out of memory basically to reconstruct and then we also obfuscate all the code that we load into memory to make it more difficult as well. So yeah, if the attacker gets stuff into memory, like you're going to have a really bad day because it's a very difficult problem. So you're typically, most organizations, their opportunity for detection is during transitions. Any type of transition the attacker makes is typically when they're most exposed to detection. And a transition can be, from disk to memory. So like when an executable runs, right? That's a transition. But a transition can also be between like privilege levels. So when we go to do some type of privilege escalation, that's also a transition. And that's also often exposes us to detection, because even if you can't detect the implant, you might detect the mechanism that we're using to escalate, right? So if we do something like EFS potato, you can potentially detect that technique or that activity without actually knowing the process is malicious. Or, code injection, by hooking things like create thread, or looking for cross-process threads and thing's like that, or suspicious variants of that. That is also, when you're migrating between processes, that's a transition. When you're performing lateral movement, that's another transition. That's typically where you're the most exposed as the attacker. If you're just sitting inside a process doing nothing, very, very difficult to detect. But you basically, the attacker still has to make plays. You still have to do stuff. So it's not like the attacker can just sit in a process doing nothing. But that's typically the most difficult place to detect them. So I would prioritize detections around privilege boundaries and things like that, because it's much more difficult for the attacker to avoid those than to try to like pull their files out of memory and things like that. So hopefully that makes sense.
Thank you. That's a really good answer.
Yeah.